Good day, everyone, and welcome back to WAEC class. Previously, we have introduced static electricity, we have looked at Coulomb's law, and we have taken some questions. Now, we're looking at further concepts of electric field intensity and electric potential. In the previous class, we said that electric field intensity E can be equal to force divided by charge. Now, remember we said that electric force is equal to KQ1 Q2 over R squared. So I can rewrite electric field intensity as saying E is equals to Q over R squared. This is almost looking like Coulomb's law. This is almost looking like Coulomb's law, but the basic difference between this one and Coulomb's law is that in Coulomb's law, you're having Q1 Q2 over R squared. Here you're having E is equals to KQ over R squared, where Q is the charge. So electric field intensity is force divided by charge, or it can be KQ over R squared, depending on it's depending on the question. But there's also something called electric field potential. Generally, the electric field potential at a point in the electric field is defined as the work per unit charge at that point, or the work done in bringing a charge from infinity to that point in the electric field. I repeat, electric field potential at a point in the electric field is the work done in bringing a unit positive charge from infinity to that point in the electric field. That's electric field potential. The symbol we use for electric field potential is V, and it can be written as minus W infinity divided by charge. This is just a mathematical expression for electric field potential, where this W infinity is representing the work done bringing the charge from infinity to that point. Furthermore, I may have 2 points in the electric field, so that here is point A and then here is point B. I may be asked to calculate for the electric field potential difference, and this is why there is potential difference. The work I'm going to do to bring a unit positive charge from infinity to this point will be quite different from the work I'm going to do to bring a unit positive charge from infinity to this point. So the electric potential here and the electric potential here will not be the same. Hence, between these 2 points, there is an electric field potential. Therefore, I can say that the electric field potential between these 2 points, I can say that the electric field potential difference between these 2 points can also be V is equals to work divided by charge, where this is now the work done between these 2 points and then this is the charge. So this is an expression for electric field potential, and this is a very useful equation in solving questions. This is just an expression. It's an equation that we don't use to solve questions. This is what we use in solving questions. Now, I can also rewrite electric field potential as KQ over R. Again, this is almost looking like this. The difference between this and this is that here there's R squared, here there's no square, just R. And the student can easily mix it up with Coulomb's law. Coulomb's law is KQ1 Q2 over R squared. Both of them, we're having one charge. While for electric field intensity or field strength, we're having one charge, and of course there's a square. For electric field potential, there is no squared. Having said all of this, there is not a relationship between electric field intensity and electric field potential. I'll show you that relationship. If you check, recall I said that E is equals to KQ over R squared. Mathematically, I can rewrite this as saying E is equals to KQ over R times 1 over R. Look at this guy, look at this equation, look at this equation. They are exactly the same. But this KQ over R rings a bell. And what is that bell? This. V is equal to KQ over R, and this is KQ over R, which means I can replace the whole of this with V. And if I do that, I'll have E is equals to V times 1 over R. Now from here, I can say E is equal to V over R. Here we go. This is now another equation that relates electric field intensity with electric field potential. You may ask me, what is the unit of electric field intensity? This is force, this is charge. So the unit can be Newton per coulomb. And you can ask me, what is the unit of electric field potential? This is electric field intensity. Now for electric field potential, it will be work over joules. The unit will be in joules per coulomb because this is work and this is charge. But that will not be the only unit for electric field intensity, because since we have already said that electric field intensity is force over charge, and we have also further said that electric field intensity is electric potential divided by distance, I can say that electric field intensity, the unit, another unit for it will be volts per meter. So I can say it's volt per meter or Newton per coulomb for electric field intensity. Now that we have explained this concept and we now have a better understanding of this concept, let's take questions under this concept before we move to the next. Question number 3 on electrostatics. Now in this question, it says, calculate the force acting on an electron of charge 1.6 10⁻⁻19 coulomb placed in an electric field of intensity 10⁸ volts per meter. Now when I say place an electric field of intensity, they have given us E. And we know what E is. E is 10⁸ volts per meter. And they have given us the charge, which of course is the charge of an electron. And it is 1.6 10⁻⁻19 coulomb. So the question will be, there are two formulas. As a matter of fact, there are 3 formulas for electric field intensity. There is E is equals to F over Q. There is E is equals to V over R. And there is E is equals to KQ over R squared. Now you may be wondering, which of them am I going to use? In this question, they're asking us for force and they're giving us charge. Asking us for force, F, they are giving us charge, Q, and we know E. So basically, I'll just know exactly what I'm going to do. I'll know that it is E that is equals to F over what? Q. This is what I'm going to use. I'm looking for force. So I'll make this force subject to formula. Very easy, by cross multiplying. And if I cross multiply, I'm going to have F is equal to QE. Now, Q is charge, E is the electric field. So from here, I'll have 1.6 times 10⁻⁻19 times what is my, that is my charge, but what is my electric field intensity is 10⁸8. From here, this is something I'm saying 1.6 times 10⁻. This is 10, this is 10, that's why I picked 1 from the law of indices. Then I have to add up the power. -19 plus 8 will give me -11. -11 Newton, 1.6 times 10⁻⁻11 Newton. And that's option A. Let's look at another question. Question number 4 on electrostatics. 2 parallel plates at a distance of 8.0 times 10⁻³ meters apart are maintained at a PD of 600 volts with the negative plate earthed. What is the electric field strength? What is the electric field strength? So here they ask us for electric field strength. They gave us the distance and they gave us the potential difference, which is V. So the question will be, what formula am I going to use? I'm going to use the formula that relates electric field strength, E, and electric potential difference, or electric potential, V. And that formula is E is equals to V divided by R, where R is representing our distance. So since we are looking for the electric field strength, which is our E, then I will say E is equals to, what is our V? Our V is 600 volts divided by, then our R is 8.0 times 10⁻⁻3. If I say 600 divided by 8.0, this should give me 7,500 volts per meter. You know, I can use volts per meter. Sorry, this should give me 7,500 volts per meter. So that is about 75,000 volts per meter. Know that I can use Newton per coulomb or volt per meter for electric field intensity. But since this one is the one that relates electric field potential and distance, it's volts per meter, and that is our unit. And that would be option D. All right, welcome back to real class. My name remains Engineer Shego, and now we'll be talking about electric line of force. What are electric line of force, you may wonder? Electric line of force are imaginary lines along which a free positive charge would move if placed in an electric field. There are some characteristics of electric line of force that you should know. We should know that electric line of force starts from a positive charge and terminates in a negative charge. This is a positive charge and this is a negative charge. You see these lines that I'm drawing here, they are coming out, the arrow is pointing outwardly from the charge. Right here, the arrow is pointing inwardly to the charge. You should know that if I were to have a charge, I would not be seeing all of these lines. Like I said, they are imaginary lines. There is the direction along which a free positive charge will move if placed in an electric field or if placed close to a charge. Now, this is two positive charges brought close to each other. Recall that we said in our previous class that the law of electrostatics, one of the fundamental laws of electrostatics, states that like charges will repel and unlike charges will attract. These are like charges. You see the way the electric line of force are pulling away from each other. They are not touching each other. So two positive charges will repel each other. Over here, we have two negative charges, and the line of force is also behaving somewhat similar to this. They are not touching each other. They are bending away. However, in this place, you see that this is a positive and this is a negative charge, and you see the way the lines of force are arranged, starting from a positive charge and terminating in a negative charge. There are other characteristics of electric line of force. I've already said that electric line of force are imaginary, and I've already said that electric line of force start from a positive charge and terminate in a negative charge. In a uniform electric field, I should also add this, that in a uniform electric field, the electric line of force are straight and parallel. Another characteristic of electric line of force is that they do not cross path. What I mean is this: you will not see this line. If you check all of this line, they are not crossing each other. One line is not coming like this and the other one is not coming like this. They do not cross each other. So I can say that electric line of force do not cross path. If they do, the electric field will have various direction at a single point, which is not so. Therefore, electric line of force do not cross path. So these are some of the characteristics of electric line of force that a student preparing for JAMB or WAEC should know. In our next class, we will be introducing capacitors.